this realm of measure of central tendency, which is how does data gather around a center point of a data set. Now this is the easy stuff. This is what many of you should have in the back of your brain. You've heard the median, you've heard the mean, and so forth. So this is somewhat familiar, although it's in a different context. All right? So we look at the measure of central tendency. We're going to look at the mean, we're going to look at the median, and we're going to look at the mode. The formula, this is one of the great statistical formulas that is absolutely meaningless in a sense, because in most of the cases when you read a statistical text, you see all this stuff in here, and really all you need is, you don't need that, you don't need that, and you don't need this. All you need is the sum of x divided by n. All that other stuff, most of the time in what statistics happens is that you have a person who writes a statistical book for another professor to show them how smart they are, not for a student. Okay, so that's why I wrote the Statistical Journey Taming of the Skews, so it actually spells this stuff out. So we're going to be talking about the mean, we're going to talk about the median, which is the exact center point of a data set. It has to be rank ordered from high to low or low to high. It's a lot easier if you rank it high to low, just as long as it's ranked. So if you have an odd data set like 6, 5, 4, 3, 2, the median is going to be the exact center point, which would be 4. If you have an even data set, what you do is you take the center 2 and take its average, so you have 3 above it and 3 below it. Okay? Now, the computer will do all that, which, again, it's one of those things you need to know. And then mode is the most frequently occurring data point in the whole data set. Now, the uniqueness of the central tendency is that when the mean, median, and mode approach the same number, or actually are the same number, you have a normal distribution because their location will be at the top. So when you look on a computer printout and you see how close the mean, median, and mode, the closer those numbers are to being identical, the closer that shape is to being a normal distribution. Okay? That's just kind of a quirk there. Then there's a thing that is a property of the mean. It's called a mean absolute deviation, or what it says is the sum of the deviation from the mean must equal 0. Now, when we go to this next data set, it'll become a little more clear. So we have a group 1x, group 2y. We have a data set for each one of them, 72, 73, 76, 76, 78. 67, 72, 76, 76, and 84. So we look at this data set and we see that the sum for each of the groups are the same. Okay? We see that there's 5 in each of the groups. We also now see that the mean for each group is 75. So it's 375 divided by 5 for each group, which gives us a mean of 75. And we also see that the sum of the deviation from the mean equals 0. Now here's how it works. The sum of the deviation, once I find the mean of a group and I subtract it from each data point and put it in the column here, the sum of that column must equal 0. That's the sum of the deviation from the mean. It's a property of the mean. It signifies that there are numbers above the mean and numbers below the mean. So if I have the mean of 75, I subtract it from 72, I get a negative 3. If I subtract it from 73, I get a negative 2. If I subtract it from 76, I get a 1, and a 1, and then from 78, I get a 3. If I add that column together, it comes up 0. It's a property of the mean. Same thing at this side over here. If I subtract 75 from each data point, the sum of that column equals 0. Now, yes?
So if it doesn't equal 0, you did something wrong?
If it doesn't equal 0, you've done something wrong, or you didn't carry out the decimal points as far as it can go. Now, years ago in our Congress, it was one of those things because people are ignorant about statistics. Now, ignorance means you don't know a whole lot about it and you need to find out about it. Stupid is different from being ignorant. You know, if I'm a little kid and I put my hand on a hot stove the first time and I get burned, that's ignorance because I didn't know. Stupid is when I do it again. Okay? Now, Congress reported, one of the congressmen got up and said, our state was above the national average on the national test. Fantastic. By the time everything got done, every state, or every representative from every state reported that their state's educational scores were above the norm, which is mathematically impossible. And of course people were going, oh wow, what a wonderful group, everybody's done so well. And it was a fabrication because every state can't be above the state norm. It violates the property of the mean absolute deviation. And because the property is when you sum the difference, it has to equal 0 because there has to be some scores above it, some scores below it. Not every score is above it. That only happens in one place, and it's called Lake Wobegon. And so during break, you need to look up Lake Wobegon and find out what it is. All right, so we keep going here. The mean absolute deviation, the median for each group is 76. The mode for each group is 76 because it's the most occurring score. So when we start looking at this, what separates the difference of the two groups? Everything's the same. What separates? What's different about the two groups? Good. It's how they vary.
Yeah, how they vary.
How they vary, because one group has more variability than the other group. So when we move into variability, it is how data is dispersed throughout a data set. Right? The other one was how does the measure of central tendency is how does data congregate around a center point. Variability is how data is dispersed. Okay? So the ones we're looking at is the range, which is the difference between the highest and lowest numbers in the data set. The problem with the range, it's a good snapshot. It's a good snapshot. But if I had 1 million numbers and I only use the highest and lowest, I throw out 998,900 and whatever, all but 2 data points. I'm only using 2 out of 1 million. So the rest of it is immaterial. So it's a good snapshot. Businesses use, or manufacturing environments use the range chart to kind of get an idea of the variability of their production line. So it's kind of a good indicator. Variance, there's that neat little formula there that I put on the board here a little bit ago. And then what we're familiar with mostly is the standard deviation. And notice that it has the same formula except one thing, which is the square root. So in the essence, the variance is the square of the standard deviation, and the standard deviation is the square root of the variance. So when you go through the formula, the next to the last step in calculation is the variance. The final step would be the standard deviation. So when we look at our data set, and we start seeing the x variable and the y variable, we start plugging these numbers in because that's the numbers we need. All right? The only difference is going to be the sum of x squared and the sum of y squared. Notice the difference in them. So as we go through the formula here and we start plugging in numbers, as we go down the line, you start seeing now the variance is going to be 4.8. Does that tell me anything? All right, it's not a large number, so it's not a whole lot of variance. Well, let's make it the last step, which is the standard deviation of 2.19. Now we get into the distributions of all of this in a little bit. Once I find the mean and the standard deviation, I can plot data on a standard normal distribution. And its range is 3 on the front end to -3 on the left end. So 2.19 tells me it's 2.19 standard deviations on the positive end. So in group number 2, if we follow, notice that the only difference is this one, 28,149 to 28,281. We kind of go down the line here. We see now the variance is 31.2 compared to 4.8. So in relationship, group number 2 is over 7, close to 8 times the variance. So I can make that comparison. And then when I get the standard deviation, it's 5.59. Well, the range is only 3, so I know it's way on the outlier part. It really doesn't conform to the norm in this case. But it's a little over 2 times the standard deviation of group number 1. So I can make that comparison that group 2 definitely has more variability in the scores than group number 1. So when you start looking at the variability and you start looking at the measures of central tendency, how do they enter in on the distribution? So we start looking at the distributions. Basically what you have are only 2 types. You got 2 types of distribution. You got one that's a normal distribution, and if it's not normal, it's going to be skewed. Now there's a wide variation of skewed distributions, but there's only one normal. All right? That's when the mean, median, and mode are the same number. If one is off by 100th, it's not normal anymore. It's close, but it's still skewed, albeit slightly skewed. There's only one normal distribution, okay? And when you start looking at the normal distributions, these are all normal distributions, okay? They have different heights. In this case, they're also symmetrical, standard normal, and z-normal. But the definition of a normal distribution is if I cut a line down the center and fold it, the right half is going to be the mirror image of the left half. That's the definition of normal. So if I'm off just by a little bit, then albeit it's not, not skewed a whole lot, but it's not going to be the mirror image of that. And so we start looking at this one and then draw a line down these, you see that they're still normal distributions, although the shape is different. So the measures of central tendency determine the normality of the distribution, but the measures of variability determine its look, its shape. In other words, this one is called mesokurtic, but it falls under the category of kurtosis. Kurtosis, that sounds like a foot disease. Kurtosis is what the distribution, how it's peaked. That's what kurtosis is, how it's peaked. So in this case, this one that we all know and love is called mesokurtic. It's actually the bell curve, the bell shape, the one that we do all about. It's the middle peak.
It's just right.
This one is called leptokurtic, which is high peaked. And what it signifies is the fact that the variability is so small that it scrunches the distribution together. Okay? So there's not much difference between the third standard deviation data point and the mean. And then the last one is platykurtic, which means low peaked, and it basically signifies that a distribution where the variability is very large and it stretches that distribution, giving it a flat shape. So we start looking at these types. The mean, median, and mode determine normality of the distribution and what and how they're put together, and the variability determines its shape, whether it's going to be middle shape, flat shape, or high peak. Then, if it's not symmetrical, which is what these are, then it has to be asymmetrical or skewed. And we start looking at skewed. There's only 2 types, again, albeit a lot of variation in that, but there's one that's called negatively skewed distribution, because the tail of the distribution points toward the negative end of the number line. And in that case, remember when I said the location of the mean, median, mode are at the center, at the top? Notice the location of the mean, median, mode in a negatively skewed distribution. The mode being greater than the median, which is greater than the mean. So that 3 different locations. So an example of a negatively skewed distribution in this case would be a test that would be way too easy. Right? Because the bulk of the scores fall at the high end. And there's not too many scores at the low end. Okay? It would also signify, if you were looking at income tax, January, February, March, April, that not too many people file here, but as you approach the April deadline, a whole lot of people file. So it would also be considered a negatively skewed distribution. The other one is a positively skewed distribution. We start looking at, because the tail of the distribution points toward the positive end of the number line, and notice the location of the mode, median, and mean. The median is greater than, or excuse me, the mean is greater than the median, which is greater than the mode. So when you see numbers like this on the computer screen, if the mean is greater than the median, which is greater than the mode, you have a positively skewed distribution. On the other end, if the mode is greater than the median, which is greater than the mean, then you have a negatively skewed distribution. So in this case, what you would have would be kind of like a ticket sales for a rock concert. So ticket sales go on here, that's where you have your bulk, and as the time goes on, people buy less and less tickets as they go there, because tickets are already sold. So it would be more of a positively skewed distribution. It would also signify a test that is way too difficult, because the bulk of the scores would be on the low end of the grading scale. So that would be another example of that. In putting all this together in a distribution type situation, I said before that the range of the normal distribution is from 3 standard deviations above to 3 standard deviations below. In that realm, when you start looking at it, roughly 68% of the scores are going to be located between 1 standard deviation above the norm and 1 standard deviation below the norm. So I said, if I had a data set of 100 and I got the mean and the standard deviation, I can plot it. 68% of those scores are going to fall within 1 standard deviation. 95% roughly is going to fall within 2, and all but a few, almost all the data is going to fall within 3 standard deviations. Again, once I find the mean and the standard deviation of that, I'll be able to plot it on here, and holding these percentages true will demonstrate normality of that distribution. Notice that it's not 100% because the remaining falls outside, either on the upper end or the lower end. And what these constitute are called outliers. These are data points that are basically belches and blurps or whatever it is that don't conform to the norm, and they fall outside of that realm. So that's why you have somebody that, when I said 5.5 standard deviations, all right, it would be out here, but it wouldn't conform to the normal data set. It would be considered an outlier because you don't have that many that fall within that realm. So here's how you plot on a data set. If I have a data set, you have to understand, in a normal distribution, it has a formula of mean equals 0 and a standard deviation of 1. So if I add the standard deviation to the mean, I get 0 plus 1 is 1, plus 1 is 2, plus 1 is 3. Minus 1 is negative 1, minus 1 is negative 2, plus minus 1 is negative 3. So that's the formula. So if I have the complete data set of 100, and it has a mean of 50 and a standard deviation of 10, my mean now becomes 50. What is 1 standard deviation above? 50 plus 10. 60 plus 10. Plus 10. Minus 10. 40 minus 10. Minus 10. Let's see if you're right. Oh my gosh.
Right.
Amazing. All right, so that's how you plot it. So I know that with that data set of 100, with a mean of 50 and a standard deviation of 10, that 99.7% of all the data within that data set is going to fall between 20 and 80. Okay? 66% or 68% is going to fall between 40 and 60. 95% is going to fall between 30 and 70, and virtually the rest of it is going to fall between 20 and 80. All right, I have another data set of 100, and I have a mean of 50 and a standard deviation of 2. Mean of 50, standard deviation of 1 is 50 plus 2, 52 plus 2, 54 plus 2, minus 2, 48, minus 2, 46, 44. So now 99.7% of that data is going to fall between 44 and 56. Wow, isn't that exciting?
Very.
Yes, give me more.
There you go. Okay. Now look at these two data sets here. What we're looking at is the variability of the two. All right. So we can determine the height. If we look at this one and the variability, this one's going to have a little more variability than this one because of the range. Okay, 95% of the scores as they go fall between it. The range is going to be between 20 and 80 of this sequence here. All right, so we're looking at a range of 60 between that group. All right, this one has a range of 12. So this one has a little more variability than this group here. So this one's going to start approaching the platycurtic, while this one is going to start approaching the leptocurtic, because there's not much difference between the third standard deviation of 56 and the mean of 50. There's a lot of difference between the third standard deviation of 80 and 50 in that sense. Now, putting it all together, this is what's exciting. We have the data type, the data strength, and the data test. We have the parametric, we have the non-parametric. We have the ratio, the interval, the ordinal, and the nominal, and then we have the dividing line there. Dividing line between the parametric and non-parametric. Nominal, ordinal, non-parametric, interval, ratio, parametric. These are the statistical tests that we're going to be talking about in the parametric realm here. One sample z-test, one sample t, independent t, dependent, one-way analysis of variance or an ANOVA, Pearson correlation, repeated measures ANOVA. Those are all tests associated with parametric that have to follow stringent assumptions. For every parametric procedure, there's a non-parametric counterpart. So in this case, if we have to go across, we have to look at the non-parametric procedures of ordinal. So the counterpart for an independent t-test would be the Mann-Whitney U. The counterpart for a dependent t-test test would be a Wilcoxon T. Counterpart for a Pearson correlation would be the Spearman-Rowe. For the dependent, for the ANOVA would be the Kruskal-Wallis, and for the repeated measures would be the Friedman-ANOVA of ranks. So those would be if we were looking at testing the medians. If we were testing frequency data, the other two tests we're going to be talking about would be the chi-squared goodness of fit and the chi-squared test of independence. Mode is associated with nominal strength, median with ordinal, and mean with interval and ratio strength. And then here are the assumptions that I was talking about a little bit ago. Normally distributed variable, homogeneity of variance, null hypothesis of true, which we'll get in later, and least interval strength data. Those are the stringent assumptions that we have to assume in order to make this all work in the parametric realm. And then finally, when you put all this data into a computer a statistical program, what you get will be a printout looking something like this. You'll get the mean, you'll get the standard deviation, you'll get how many numbers are in there, you'll get number missing if you have a problem, you get the variance of each group, you get the range of each group, you get the sum, which would be the sum of x or sum of y, you get the sum of squares, which would be the x squared or y squared column, you get the skewness, and if you have a positive number, it's positively skewed, and a negative number, it's negatively skewed. So it's the asymmetrical distribution. If skewness is positive or negative, the data is skewed to the right or to the left. The larger the number, the greater the skew. Notice that this number is not very large, 0.272, albeit it's skewed a little bit. When we start looking at the mean and the median and the mode, those numbers are pretty close together. So that's why we have a measure of skewness, but not a whole lot. Then you get this thing of kurtosis, which is how peaked the distribution is. So when kurtosis equals 3, it's a normal height distribution. When it's greater than 3, it's peaked, and when it's less than 3, it's flat. So what we have here is something that's what, less than 3? So we're going to have more of a flat-looking distribution, and if we put it all together, it will come up a flat-looking distribution. Then you get the median, and then you get the mode. So putting all this data together in a computer analysis, and I'll show you how to do it on the stat program here. Once we enter it into the data, enter the data in the computer, you get this nice little printout here, and you start putting it all together. So that's the end of this section.